Somewhere far beyond Neptune, a planet may be drifting through the dark, massive enough to shape the outer solar system, yet too distant and too dim for us to see. Planet 9 could be real, and the strangest part is not that it might exist, but that it could have been hiding in our own cosmic backyard this entire time. For more calm space documentaries like this, please like the video, subscribe to the channel, and settle in for the journey. Far beyond Neptune, the solar system does not end in a clean line. It thins, it loosens, it spreads into a region where the sun still rules by gravity, yet gives very little warmth and very little light. This outer domain is part of the same planetary system that holds Earth, but it does not resemble the bright inner neighborhood where planets are easy to name and easy to follow. Out there, distance becomes the main condition of existence. Objects move through enormous volumes of darkness, separated by expanses so wide that even a large world can remain only a faint idea for a very long time. The sun is still the center of this system, and every known planet remains bound to it. But the outer solar system reaches far past the last major planet. Beyond Neptune lies a realm of icy bodies, scattered debris, and long, silent orbits. The farther outward the system extends, the less crowded it seems. It is not empty in an absolute sense, yet it behaves like emptiness. Matter is spread thinly. Light weakens. Motion slows when measured against the immense scale of each path. A place can belong to the solar system and still look almost indistinguishable from deep space. This is the setting in which the idea of Planet 9 remains scientifically plausible. Researchers do not describe such a world as confirmed. NASA continues to present it as a theoretical planet, inferred from its possible gravitational effects rather than seen directly. If it exists, it is not thought of as a near-hidden neighbor just beyond Pluto. It is instead placed in a remote outer region, far beyond the familiar planetary arrangement, on a path so large that a single orbit around the Sun could take many thousands of years. In that environment, ordinary expectations about what should be easy to find begin to fail. The human eye, and even the modern telescope, works under limits that become severe in such a place. A planet does not shine by itself unless it still gives off internal heat. In visible light, it is usually seen because it reflects sunlight. That basic fact matters greatly in the outer solar system. As sunlight travels outward from the sun, it spreads across a larger and larger sphere. By the time it reaches extreme distances, the amount of light falling on any one patch of cloud, ice, or rock becomes very small. Then the reflected light must travel all the way back across space before any telescope can gather it. What remains is faint beyond ordinary intuition. This is one reason a distant planet in the solar system can be harder to see than a planet orbiting another star. A faraway exoplanet is often found not because astronomers image it clearly as a bright disk, but because it slightly dims its star, tugs on its star, or glows in special conditions. Distance alone does not decide difficulty. Method decides difficulty. In the outer solar system, the search is not for a planet crossing the face of a star on a short repeating schedule. It is for a dark body, moving slowly across a vast background, with only weak sunlight to reveal it. Nearness in cosmic terms does not guarantee visibility. The scale of the search area also shapes the problem. The night sky is immense, and the region where a distant planet may lie is not a narrow point marked in advance. It is a broad and uncertain zone spread across many possible positions. A telescope that sees faint objects usually covers only a limited patch of sky at one time. A telescope that surveys a wide area may not always go deep enough to catch the dimmest target. Astronomy often works by balancing width against sensitivity. In the case of a distant outer planet, both are needed together, and that combination is demanding. The outer solar system also changes human intuition about motion. The known planets of the inner and middle system shift in ways that can be followed over manageable spans of time. A very distant planet would behave differently. It would still move under the sun's gravity, yet from Earth its progress across the sky could appear extremely slow. Night after night it might seem almost fixed. Month after month it might drift so gently that it could be mistaken for a far more distant source of light, unless careful comparisons are made. A world can remain hidden not only because it is dim, but because it does not announce itself through brisk motion. Cold deepens this obscurity. Far from the sun, surfaces and cloud tops receive so little energy that they settle into an environment of extraordinary low temperature. Such a planet would not resemble the bright gas giants as they appear in ordinary images made from much closer range. It would live in a muted state, with weak illumination and long seasons that stretch across spans longer than recorded human history. Its year would be so extended that no person could casually watch it, complete even a small fraction of its orbit. In practical terms, the outer system asks astronomy to study change that is real but very slow. For this reason, the far edge of the solar system remains a frontier not because science lacks skill, but because nature has arranged the conditions there to conceal large bodies surprisingly well. The system is large beyond instinct. The light is poor. The possible hiding places are many. The motion is gentle. The targets, if present, are few. Every part of the problem widens the search and lowers the signal. This is why the idea of Planet 9 begins not with a picture, but with a setting. Before any argument about particular objects or surveys, there is the simple physical fact that the sun's domain extends into a remote and dim expanse where seeing is difficult by definition. The outer solar system is not a bright gallery waiting to be inspected one world after another. It is a sparse gravitational landscape in which distance strips away the usual clues. A planet there would still be real, still bound to the sun, still part of the same system as Earth, yet hidden within conditions that naturally resist quick discovery. In that wide darkness, absence of an image does not by itself mean absence of a world. Beyond Neptune, the broad outer frontier begins to gather into a more recognizable population of bodies. This region is known as the Kuiper Belt, a wide zone of icy remnants left from the early formation of the solar system. NASA describes it as a donut-shaped region beyond Neptune, home to Pluto, other dwarf planets, and countless smaller objects. Yet the farther outward one looks within and beyond this belt, the less it resembles a simple ring of evenly placed worlds. It becomes irregular and patchy. Some bodies move on calm paths. Others follow elongated routes that carry them far from the sun for most of their long lives. In this far Kuiper fringe, the outer solar system begins to reveal itself not as a neat edge, but as a historical record written in orbit. These distant bodies are often called trans-Neptunian objects, meaning objects whose paths lie beyond Neptune. The term sounds technical, but the meaning is simple. They are small worlds of ice and rock living in the cold beyond the last giant planet. Many are dark, many are ancient. Most are too small and too far away to show detail in powerful telescopes. They appear as moving points of light when they can be detected at all, yet their importance is much greater than their size might suggest. They are among the least altered leftovers from the era when planets were still assembling. They preserve the conditions of a young solar system in a way that the warmer inner planets do not. In the inner system, sunlight is stronger, collisions are more frequent, and planetary geology can erase very old surfaces. In the far Kuiper fringe, change is slower, temperatures remain extremely low, chemical activity is limited. A body may spend billions of years in deep freeze, disturbed only occasionally by a collision or a slow gravitational shift. Because of this, distant icy objects can act like stored material from an early archive. Their compositions, sizes, and orbital shapes help astronomers infer how the giant planets once moved, how small bodies were scattered, and how the outer system acquired its present structure. This region is not densely packed in the ordinary sense. Popular images can make belts in space look crowded, but the real Kuiper belt is spread over an immense volume. Individual objects are separated by large distances. A spacecraft can travel through it without weaving among nearby hazards. What gives the region its scientific richness is not local crowding, but population. There are many bodies, and together they form patterns. When enough of them are discovered and their orbits are measured, the outer solar system begins to show large-scale structure. It becomes possible to distinguish objects that remain under Neptune's strong long-term influence from those that carry signs of ancient dynamical upheaval. The far fringe matters especially because it is where ordinary planetary organization begins to weaken. Closer to Neptune, many objects are linked to the giant planet through resonances, stable timing relationships in orbit that help keep them on repeating paths. Pluto is the most famous example of this kind of arrangement. Farther outward, however, there are bodies whose nearest approach to the Sun remains so distant, and whose overall paths are so extended, that Neptune no longer seems sufficient to explain every detail of their present motion. Some may have been lifted outward through gradual interactions over immense spans of time. The farther fringe therefore acts like a transition zone between the known architecture of the solar system and a more weakly mapped outer domain. Observationally, this population is difficult to study well. A distant icy body is usually found near the part of its orbit where it comes closest to the Sun, not because that is where it spends most of its time, but because that is when it is brightest and easiest to detect. This means the discovered sample is not a simple picture of what is truly out there. It is a filtered sample shaped by visibility. Telescopes tend to find objects when they are in favorable positions, in accessible parts of the sky, during seasons and survey programs that happen to cover those areas. Astronomers therefore treat every discovery with care. A pattern in the known objects may reflect nature, or it may partly reflect where and how people have looked. Even with that caution, the far Kuiper fringe remains one of the most informative regions in planetary science. Each new distant body expands the map of possible orbital histories. Some objects follow paths that remain comparatively flat with respect to the solar system's main plane. Others are notably tilted. Some are scattered inward and outward across large ranges of distance. Some remain detached from strong encounters for spans long enough to seem almost secluded. Together, they reveal that the outer solar system is dynamically textured. It is not a smooth shell of ice. It is a collection shaped by migration, scattering, resonance, and time. The physical nature of these bodies adds another layer of meaning. Many are mixtures of water ice, rock, and frozen substances such as methane, nitrogen, or carbon monoxide, depending on their size and thermal history. Larger dwarf planets can retain bright frosts or thin atmospheres under the right conditions. Smaller bodies tend to be darker and less complex in appearance. Radiation gradually alters exposed surface material over immense times, reddening or darkening it. Yet despite surface aging, these worlds still remain witnesses to early solar system conditions because they have not been melted and recycled in the way large active planets have. The far Kuiper fringe is important because it quietly preserves order within apparent disorder. Every long orbit carries information. Every unusual distance from the Sun hints at past gravitational shaping. Every newly found body improves the statistical view of a region that remains thinly sampled. Researchers do not rely on one object alone to understand this distant zone. They read the population as a whole, always aware that incompleteness remains part of the problem. In this sense, the far fringe beyond Neptune serves as a bridge between visible worlds and inferred structure. It contains bodies small enough to escape notice, yet numerous enough to outline the hidden design of the solar system's edge. Their faintness slows discovery, but their orbits endure. Over time, careful observation turns these distant icy remnants into a map. Not a complete map, and not a final one, but one that steadily clarifies how the outer solar system is arranged. In the dim reaches beyond Neptune, small objects become the first readable traces of a much larger gravitational landscape. Within the far outer population beyond Neptune, a small and unusual company of bodies begins to stand apart from the rest. These are the objects whose paths do not bring them back into the region where Neptune exerts its strongest shaping power. They are often described as detached. The word has a plain meaning. Their orbits appear separated from the direct gravitational reach that explains many other distant icy bodies. They still belong to the solar system. They still circle the Sun. But they do so along routes that seem lifted away from the ordinary traffic of the known giant planets. Sedna is the best-known example of this quiet company. It follows one of the most remote orbits known among named solar system bodies. At its nearest to the Sun, it remains about 76 astronomical units away. At its most distant, it travels to roughly 1,200 astronomical units. Even near its closest approach, it stays far beyond Neptune. That single fact gives Sedna its importance. Neptune circles at about 30 astronomical units from the Sun. Many trans-Neptunian objects come close enough to Neptune over long spans of time for repeated gravitational encounters to stretch, tilt, or scatter their orbits. Sedna does not. Its path remains so distant at perihelion, the point where an orbit comes closest to the Sun, that it is difficult to attribute its present route to ordinary close interactions with Neptune alone. Sedna therefore occupies a special place in the outer solar system. It is not simply another icy remnant beyond Pluto. It is a sign that the outer system contains objects whose histories may not fit comfortably within the better understood architecture of the Kuiper belt and scattered disk. The scattered disk includes bodies that have clearly been thrown onto elongated paths through past interactions with Neptune. Their orbits often still dip back toward the region of the giant planets. Detached objects differ because their nearest returns remain too distant for that explanation to feel complete. They seem to preserve the mark of a force that acts differently, or at different time, or under different conditions. Sedna is not alone. Another important example is 2012 Victor Papa 113, another distant body with a large orbit and a notably high perihelion. It does not travel as far out as Sedna, but it shares the same central quality of detachment. It remains too remote at closest approach to fit neatly into a picture dominated by Neptune scattering. As more of these distant bodies are found, they begin to form a category often informally called sednoids, meaning objects that resemble Sedna in their large semi-major axes and unusually high perihelia. The term is useful because it groups together bodies that occupy the same strange orbital territory, even if their exact paths differ. These objects are difficult to discover for simple physical reasons. They spend most of their time far from the Sun, where they receive very little light and reflect even less back toward Earth. A body on a strongly elongated orbit moves fastest near perihelion and slowest when far away. That means Sedna-like objects linger for immense spans in the darkest part of their paths, then pass through their relatively more detectable inner stretch only briefly in comparison. Astronomers are therefore much more likely to find them when chance sky coverage and observing depth align near the brighter part of their orbit. What is known about them almost certainly represents only a fraction of what exists. Their rarity in current catalogues does not reduce their scientific weight. A single detached object already indicates that the outer solar system contains pathways into this distant state. Several such objects suggest that the pathway is not a singular accident. The challenge is to explain how such orbits arise. One possibility is that the early solar system does not always resemble the present one. In its youth, the Sun likely forms in a stellar nursery, surrounded by other young stars. Close stellar passages in that crowded environment could perturb distant icy bodies, gently lifting perihelia and leaving some objects stranded on remote elongated paths. Another possibility is that the giant planets migrate in the early system, reshaping the small body reservoir in more complex ways than a static modern model would imply. Yet another possibility is that an additional massive body far from the Sun contributes to the long-term sculpting of these detached orbits. Observations indicate that more than one class of explanation remains viable. It remains uncertain which process, or combination of processes, accounts for the full detached population. What matters at this stage is not to assign certainty where none exists, but to describe the observational condition clearly. Sedna and its companions inhabit a region of orbital parameter space that looks difficult to reach through present-day Neptune encounters alone. That statement is narrower than a claim of proof, and more useful. It keeps the focus on the actual data. Their high perihelia are real. Their large semi-major axes are real. Their remoteness from Neptune at closest approach is real. These features make them valuable tests for models of solar system evolution. Detached objects also help astronomers separate immediate gravitational control from historical memory. A body still crossing near Neptune can have its orbit changed repeatedly over time. A body like Sedna carries a quieter record. Its path appears less exposed to ongoing disruption by the known giant planets. In that sense, it preserves a fossil orbit, not frozen in every detail, but more insulated from ordinary outer planetary traffic. Such bodies are precious because they may retain evidence of ancient events that other populations have partly lost. Their calm outward appearance conceals a demanding observational problem. To measure a long orbit well, astronomers need repeated observations across many years. Distant objects move slowly against the background stars, and early orbital estimates can carry large uncertainty. Each additional observing season improves the orbit, sharpens the classification, and clarifies whether a body truly belongs among the detached population. This gradual accumulation of precision is part of why the sample grows slowly and why interpretations remain careful. Sedna's quiet company therefore marks a threshold within the outer solar system. These bodies are not simply far away, they are far away in a particular dynamical sense. Their nearest approaches remain elevated above Neptune's strong present reach, and that makes them stand apart from more familiar trans-Neptunian populations. They are rare, faint, and difficult to track, but they hold disproportionate importance because they show that the solar system's distant architecture includes orbits that seem to require more than ordinary scattering. In their silence, they preserve one of the clearest signs that the outer system still contains a history not yet fully explained. In the far outer solar system, the strongest reason scientists begin to speak of a hidden planet does not come from seeing a new body, it comes from direction. A small number of the most distant known objects appear not only remote, but arranged in a way that seems unexpectedly ordered. Their paths through space do not point in every possible orientation with equal freedom. Instead, several of them appear to share similar directions in the way their long orbits are laid out around the Sun. This is the observation that gives the Planet 9 idea its original force. An orbit is more than a distance and more than a travel time. It also has a shape and an orientation. Two bodies may both follow long-stretched paths far beyond Neptune, yet those paths can be turned differently in space. One may come closest to the Sun on one side of the solar system, while another reaches its nearest point in a very different direction. If enough objects are found, and if their orbits are truly independent, astronomers generally expect their orientations to be spread out over time. Long periods of motion and repeated gravitational disturbances tend to mix directions rather than preserve a neat pattern. That expectation makes any sign of alignment scientifically interesting. The early Planet 9 argument begins with this point. A group of very distant bodies, especially those with large elongated orbits and remote perihelia, seem to cluster in the directions of their nearest approaches to the Sun. Perihelion is the point in an orbit where an object comes closest to the Sun. For these distant bodies, the direction toward perihelion is not a small detail. It is one of the clearest ways to describe how the orbit is turned in space. Researchers studying these objects notice that several of them seem to have perihelia pointing into a similar sector rather than being scattered evenly around the sky. The pattern does not stop there. Some of the same objects also appear to share a related alignment in their orbital planes. The plane of an orbit is the flat surface in which the body travels around the Sun. If several distant objects have orbital planes that tilt in a similar way, and if their perihelia also gather in a related direction, the combined effect is harder to ignore than any one feature alone. NASA's current summary of the hypothesis reflects this point. The proposed planet is invoked not merely to explain that a few objects are far away, but to account for why long-period Kuiper belt objects appear tilted on average, and why some of their orbital orientations seem to cluster. This is what gives the evidence its distinctive character. The case is not built on brightness, shape, colour, or atmosphere. It is built on geometry. A hidden planet is suggested because the outer solar system seems to contain a small population of objects whose orbital directions appear more organised than expected. The claim is therefore indirect from the beginning. Scientists do not say that the distant planet is seen. They say that if the pattern is real, then a massive unseen body offers one plausible way to maintain it. The word maintain is important. Orbits are not static drawings. Over very long spans, their orientations drift. They precess, meaning the direction of the orbit slowly changes under gravitational influence, in a system containing only the known planets. One generally expects distant elongated orbits to lose any apparent common pointing, unless some process continually reinforces it, or unless the pattern is temporary. This is why the clustering matters. It suggests not simply that the outer solar system once experienced an unusual event, but that a continuing gravitational influence may be shaping the present distribution. The argument becomes stronger in the minds of its supporters because the relevant bodies are not all discovered in one single observing campaign with one single instrument. The original impression of clustering survives across discoveries made at different times. That does not prove the pattern is physical, but it does make the observation harder to dismiss as a simple artifact of one telescope looking repeatedly in one patch of sky. The distant objects function like sparse markers laid across the edge of the solar system. When several markers point in related directions, astronomers begin to ask what common force might be arranging them. This kind of evidence is common in astronomy. Much of the universe is studied through influence rather than direct contact. Planets around other stars are often inferred from the motion of their stars. Dark matter is inferred from the motion of galaxies and clusters. In the same broad spirit, Planet 9 is inferred from orbital structure. The unseen body enters the discussion because the visible bodies seem to be tracing out its effects. The distant small objects act less like targets in themselves and more like test particles moving through a larger gravitational design. Even so, the evidence remains a clue rather than a conclusion. The sample of most relevant bodies is still small. A handful of remote objects can suggest order, but a handful alone cannot guarantee that the order reflects the full population. Astronomers therefore treat the clustering as statistically meaningful only with care. The core scientific question is simple in form, even if difficult in practice. Are these orbital directions truly unusual once the real discovery circumstances are taken into account, or do they only appear unusual because the known sample is incomplete? At this stage in the reasoning, the important fact is that the observed directions are what first transform a vague idea of a hidden world into a concrete orbital hypothesis. Without the clustering, there is no strong reason to place a several Earth-mass planet on a particular distant path. With the clustering, the hypothesis gains shape. The geometry of the small bodies begins to act like a rough pointer toward the properties of the unseen one. Their shared directional tendencies become the first map of a planet that no telescope has yet securely isolated. This is why orbital directions stand at the heart of the Planet 9 story. Distance alone does not imply a hidden giant. Strange individual objects alone do not imply one either. What begins to suggest an unseen planet is the possibility that several distant bodies, each faint and isolated, are nonetheless arranged by the same gravitational hand. The evidence is quiet, abstract, and indirect. It lives in angles, planes, and orientations. Yet in planetary science, such structure can be deeply revealing. At the edge of the solar system, direction becomes the first language in which a hidden planet might announce its presence. The apparent pattern in the orbits of the most distant known objects invites a natural response. It encourages the idea that a hidden planet may be guiding them. Yet astronomy rarely accepts a pattern at face value, especially when the sample is small and the search is difficult. Before any orbital alignment can be treated as evidence of a real distant world, scientists must ask whether the pattern is produced by nature or by the way discoveries are made. In the Planet 9 debate, this question becomes central. The problem of bias stands between observation and conclusion. Bias in this context does not mean carelessness or error. It means that a survey of the sky never sees all possible objects equally. Telescopes observe at certain times of year. They point towards certain regions and avoid others. They work under limits of weather, instrument sensitivity, tracking ability, and available time. Some projects go deep over a small area, others cover more sky but miss fainter targets. Some objects are easier to recover after discovery, while others are lost because they move too slowly, too faintly, or through crowded fields of stars. A discovered population is therefore never identical to the true population. It is a filtered version of reality. This matters greatly in the outer solar system because the objects of interest are faint, slow, and rare in current catalogues. A distant trans-Neptunian object is most likely to be found when it is near perihelion, where it is brightest. It must also happen to lie in a part of the sky being observed by a survey with sufficient depth. If its motion is too slight from one image to the next, it may not stand out as a moving body. If follow-up observations are not possible, its orbit may remain too uncertain for use in statistical studies. Each step between existence and confirmed discovery removes part of the underlying population from view. As a result, an apparent orbital alignment can arise in at least two different ways. It may reflect a true physical structure in the solar system, or it may reflect the regions and methods through which astronomers have searched. If surveys are more likely to detect distant objects in certain sky sectors than others, then the known sample can appear clustered even when the unseen parent population is more evenly spread. This is why the Planet 9 argument remains under active scrutiny. The issue is not only whether clustering appears in the data, the issue is whether clustering survives after the discovery process itself is modelled in detail. Researchers approach this by reconstructing the observing histories of surveys. They examine where telescopes looked, how faint an object could be and still be found, how moving sources were selected, and how follow-up rules influenced which discoveries became secure orbital detections. This work is difficult because the historical record is not always complete in the same way across all surveys. Some discovery programs publish detailed pointing histories and detection efficiencies. Others are less uniform across time. The stronger the reconstruction, the better astronomers can estimate how likely a given orbital pattern is to emerge from a uniform population seen through uneven search conditions. This is where disagreement enters. Some studies argue that once observational bias is properly taken into account, the apparent clustering of extreme trans-Neptunian objects loses much of its force. In this view, the known sample is too shaped by where astronomers have looked and how the objects were recovered to justify a confident claim of true orbital concentration. Other studies, including more recent work from Planet 9 proponents, argue that even after updating estimates of bias, the clustering remains stronger than chance would comfortably allow. The scientific landscape therefore does not contain a settled verdict. It contains competing statistical readings of a sparse and difficult data set. Such disagreement is not a weakness of science. It is science working under limited information. The outer solar system does not provide abundant bright targets. It offers a small sample drawn from a vast dark volume. When numbers are low, each new object can shift the pattern noticeably. A single discovery in a previously empty orbital direction can weaken the appearance of alignment. A few more objects in the already favoured direction can strengthen it. The debate therefore evolves as the catalogue grows. This is one reason scientists speak carefully. A pattern that looks persuasive in one decade may soften in the next, or it may become firmer as surveys improve. Bias also affects which kinds of objects enter the discussion at all. The Planet 9 hypothesis depends most strongly on the most extreme objects, those with large semi-major axes and large perihelia. Yet these are also among the hardest objects to detect and confirm. Their very remoteness makes them scientifically valuable and observationally troublesome at the same time. The bodies that matter most for the argument are often the ones most vulnerable to uneven discovery. This creates a delicate situation. The evidence depends on the least accessible members of an already difficult population. There is another layer to the problem. Different surveys do not search the sky in identical ways, and combining their discoveries into one sample can be statistically powerful, but methodologically complex. A pattern seen in the merged data may partly reflect the combined footprints of many observing programs. The more heterogeneous the sources, the more carefully the bias must be modelled. Astronomers therefore do not simply count distant objects and compare angles. They try to understand the machinery of detection behind every orbit that enters the sample. For this reason, the phrase selection effect often appears in discussions of Planet 9. A selection effect is a pattern produced not by the hidden structure of nature alone, but by the conditions under which observations are selected. The term is simple in meaning even when the calculations are not. It reminds researchers that seeing is never neutral. Every survey selects, every catalogue filters. Every map of the outer solar system is partly a map of the sky, and partly a map of human observing history. The problem of bias does not eliminate the Planet 9 hypothesis. It disciplines it. It forces the argument away from enthusiasm and toward careful accounting. The clustering may be real, it may be weaker than it first appears, it may prove robust in some subsets and less convincing in others. At present, observations indicate that the case remains open. It remains uncertain whether the apparent alignment of the most distant objects records a true gravitational pattern or a discovery pattern shaped by incomplete coverage. That uncertainty is not a side issue. It is the central reason the existence of Planet 9 remains plausible to some researchers, unpersuasive to others, and unconfirmed for science as a whole. If Planet 9 exists, its importance does not come from sudden disruption. It comes from persistence. The proposed planet is not imagined as a world rushing inward to scatter the outer solar system in a brief violent episode. It is instead treated as a slow and distant perturber, meaning a body whose gravity acts gently but repeatedly over immense spans of time in such a setting. The key scientific idea is simple. A small force, applied again and again in the right orbital setting, can gradually reshape the paths of much smaller bodies. The outer solar system moves so slowly and endures for so long that weak nudges can accumulate into large orbital consequences. This kind of gravitational shaping is familiar in planetary science. Orbits do not need direct collision or close approach in order to change. A body can alter another body's long-term path through repeated distant interactions. When the timescale is measured in millions or billions of years, even subtle effects matter. That is why the Planet 9 hypothesis does not depend on dramatic encounters with detached objects like Sedna. It depends on sustained orbital influence. The unseen planet would act less like a passing intruder and more like a quiet organizer, slowly modifying the architecture of the distant trans-Neptunian population. The proposed mechanism operates in two broad ways. One is secular forcing. Secular here means slow, long-term change averaged over many orbits. Instead of focusing on one encounter, astronomers examine how gravity gradually alters the orientation and shape of an orbit over time. Under this process, the perihelion direction of a distant small body can drift, its orbital plane can tilt, and its eccentricity, meaning the degree to which the orbit is stretched rather than circular, can be guided into preferred ranges. The important point is that the effect is cumulative. A detached object does not need to come close to the planet on every circuit. It only needs to live for long spans inside the planet's extended gravitational pattern. The other important process is resonance. A resonance is a repeating timing relationship between two orbits. If one body goes around the Sun a certain number of times while another completes a different but related number, their gravitational interactions can reinforce one another in an orderly way. This does not mean the bodies are side by side. It means their motions repeat in a structured rhythm. In the Planet 9 picture, some distant Kuiper belt objects may fall into such long-term resonant relationships with the unseen planet. Caltech's original explanation emphasizes that this kind of orbital rhythm can keep objects aligned while also helping them avoid close disruptive encounters. Repetition becomes protection as well as control. This is why the anti-aligned geometry proposed in the Planet 9 framework matters. The distant small bodies that seem clustered do not point the same way as the putative planet. Instead, in the preferred model, their perihelia tend to lie roughly opposite the planet's perihelion direction. At first glance, such an arrangement seems unstable, because one might expect repeated crossings to lead to close encounters that break the pattern apart. Yet simulations suggest the opposite. If the timing is right, resonance and secular evolution together allow the smaller bodies to remain confined in this anti-aligned structure over very long intervals. The geometry looks dangerous in a static diagram, but the moving system can preserve it. A several Earth mass planet is central to this idea because mass controls the reach and strength of the perturbation. A very small body far from the Sun would not have enough influence to organize the detached population in a coherent way. A very large planet would risk producing stronger consequences than are observed. The current Planet 9 estimates therefore tend to fall in the range of a super-Earth or small ice giant, large enough to shepherd the outer orbits, but distant enough that the process remains gradual. The latest orbital inference work from Brown and Batygin places the favoured mass near 6 Earth masses, with a wide, inclined, eccentric orbit whose long-term influence can reproduce the observed distant orbital structure in simulations. The word shepherd is often useful here, provided it is kept literal rather than poetic. In planetary dynamics, shepherding means gravitational guidance that confines motion into a preferred arrangement. The distant objects are not dragged physically through space like material in a fluid. They remain on their own orbits around the Sun. What changes is the range of orbital states they can occupy stably over immense times. Some orientations persist, others are depleted because they lead to instability, ejection, or transfer into different populations. Over time, the surviving objects form patterns. In that sense, Planet 9 would not place the orbits by hand. It would reshape the outer system by making some orbital pathways durable and others short-lived. This helps explain why the hypothesis is able to address more than one observed feature at once. NASA's current summary notes that the same broad mechanism could account not only for clustering in orbital orientations, but also for the average tilt of certain long-period Kuiper belt objects, the existence of highly inclined distant bodies, and even some retrograde populations between the giant planets. In the mechanism-based view, these are not separate mysteries requiring separate causes. They're different expressions of one persistent gravitational field acting on a thinly populated outer reservoir over long times. The detached bodies are especially important because they are the clearest long-term recorders of this sort of influence. Objects still deeply entangled with Neptune can have their paths scrambled by ongoing encounters with the known giant planets. More detached bodies are quieter dynamical tracers. Their orbits can still evolve, but they are less dominated by present-day close scattering from Neptune. That relative isolation makes them more sensitive as indicators of weak, extended forcing from a farther planet. In practical terms, they carry cleaner evidence. Even so, this mechanism remains a model, not a confirmed description of reality. It works by showing that a distant perturber can generate the kinds of orbital structures astronomers observe. It does not yet prove that such a planet exists. Other explanations may account for part of the pattern, and the true outer population remains incompletely sampled. But within the logic of celestial mechanics, the proposed process is coherent. A distant massive planet can, through slow secular forcing and long-term resonant protection, pull standard scattered objects into more detached states, preserve anti-aligned groupings, and maintain unusual tilts without requiring continual close encounters. So the Planet 9 idea becomes physically meaningful at this stage. It is no longer only a pattern in angles. It becomes a dynamical system. A hidden planet, if real, does not need to announce itself through brightness first. It can reveal itself by the way it patiently edits the outer solar system. Across millions of years, repeated weak nudges can leave a durable signature. In the deep cold beyond Neptune, that quiet persistence is exactly the kind of force that matters most. If Planet 9 exists, the path it follows around the Sun is not expected to resemble the nearly circular orbits of the major planets seen in the inner solar system. It is instead described as elongated, inclined, and immense. This orbital picture matters because it explains why the planet, even if real, does not behave like an obvious missing member of the known planetary family. It would not circle the Sun in the orderly planetary zone from Mercury through Neptune. It would move through a much larger and more rarefied outer domain, tracing a route so extended that most of its existence would unfold far from the Sun and far from the parts of the sky most often searched for nearby moving worlds. The basic idea begins with the shape of the orbit. In astronomy, an orbit can be more circular or more stretched. A stretched orbit is often called eccentric. That term means the distance between the orbiting body and the Sun changes greatly over the course of one full revolution. For Planet 9, current estimates do not place it on a gentle near circle. They place it on a long oval. This means there would be one part of the orbit where it comes relatively closer to the Sun, though still very far beyond Neptune, and another part where it retreats much farther into the dark outer solar system. The difference between those two states is central to the hypothesis. NASA's current summary presents the planet as a hypothetical world orbiting on a highly elongated path, with an average distance roughly 20 to 30 times greater than Neptune's distance from the Sun. That description captures the scale of the orbit without pretending the details are settled. Earlier versions of the hypothesis often favoured a larger orbit still, with a semi-major axis, meaning half the long width of the orbital ellipse, near 700 astronomical units. More recent modelling by Batygin and Brown suggests a somewhat tighter path may better fit the known extreme trans-Neptunian objects, with a favoured semi-major axis near 380 astronomical units and a closest approach to the Sun around 300 astronomical units. Observations therefore suggest a broad family of possible orbits rather than one final path. It remains uncertain which, if any, of these solutions matches reality. Even in the more compact modern estimates, the orbit remains enormous. Neptune circles the Sun at about 30 astronomical units. A planet with a semi-major axis of several hundred astronomical units belongs to a very different dynamical environment. Its year is not measured in decades, but in thousands of Earth years. NASA gives a likely orbital period between 10,000 and 20,000 Earth years for the broader hypothesis, while the tighter modern solutions bring that period down but still leave it within the span of many millennia. The important physical point is unchanged. This would be a planet whose seasonal and orbital timescales lie far beyond ordinary historical memory. Human civilization would observe only a minute fragment of its journey. The orbit is also expected to be inclined. Inclination means tilt relative to the general plane in which the major planets orbit the Sun. The main planetary system is fairly flat. Planet 9 is not usually modelled as lying in that same flat sheet. Instead, current preferred solutions place it on a path tilted by roughly the high teens in degrees, and older estimates sometimes allowed even larger tilt. This does not mean the planet rises far above the solar system in any absolute sense, because the solar system itself is not a rigid plate. It means the orbit is set at a noticeable angle to the familiar planetary plane. That tilt is important because it helps the hypothetical planet produce the unusual orbital structure seen among some distant small bodies. But at the level of the orbit alone, the key fact is simple. Planet 9 is not expected to move where astronomers first tend to look for planets, along the brightest and most familiar planetary corridor. The position of perihelion also matters. Perihelion is the point where an orbit comes closest to the Sun. In the current picture, Planet 9 does not come in anywhere near the giant planets. Even at perihelion, it remains very remote. That remoteness is one reason the hypothesis remains physically plausible, without obvious contradiction from direct observation. A planet can be large and still evade easy detection if its orbit keeps it hundreds of astronomical units away even in its relatively inner phase. The orbit therefore solves one basic puzzle at once. It allows the planet to be massive enough to influence distant icy bodies, while still staying far enough away to remain faint and hard to find. An elongated orbit also means the planet would not spend equal amounts of time at all distances. Kepler's laws describe how bodies in elliptical orbits move faster when they are closer to the Sun and slower when they are farther away. The consequence is subtle but crucial. Planet 9 would pass more quickly through the inner part of its distant orbit and linger much longer in the outer part. It would spend most of its orbital life not near perihelion, where it would be comparatively easier to detect, but near aphelion, the farthest point from the Sun, where its motion is slowest and its visibility poorest. This is one of the most important properties of the proposed orbit. Even if the planet exists, the odds are not especially favourable that it happens to be near the part of its path where discovery is easiest. The orbit also has an orientation in space, not just a size and shape. In the Planet 9 framework, the favoured orbital direction is related to the anti-aligned pattern seen in certain extreme trans-Neptunian objects. The small bodies do not merely suggest that a distant planet exists somewhere far out. They point toward a family of orbital orientations for it. This is how the hypothesis advances from a vague notion of a hidden world to a specific search geometry. The orbit must be large enough, stretched enough, and tilted enough to account for the observed distant structure, while also pointing in a direction that keeps the system dynamically coherent over long times. Yet none of these orbital elements should be treated as final. Each estimate depends on a limited and biased sample of distant objects, and the best fit orbit changes as new discoveries are added and dynamical models improve. The current scientific position is therefore disciplined rather than dramatic. Planet 9, if real, likely follows a long, inclined, eccentric path far beyond Neptune. It likely takes thousands of years to complete one circuit of the Sun. It likely remains hundreds of astronomical units away even at its nearest. Beyond that, the precise orbit remains a moving target of research. So the picture that emerges is not of a missing planet tucked just outside the known 8, but of a distant world on a vast and tilted ellipse, circling slowly through the dim outskirts of the Sun's gravitational domain. Its path, if it exists, is large enough to make absence of direct detection unsurprising, structured enough to leave possible dynamical traces, and uncertain enough to keep the search open. In the logic of the hypothesis, the orbit is the reason Planet 9 can be both influential and unseen at the same time. At this point in the hypothesis, the hidden planet begins to take on physical form. It is still unseen and still unconfirmed, but it is no longer only a mathematical source of orbital disturbance. From current dynamical estimates, astronomers can sketch the kind of world it is likely to be if it exists. That sketch does not describe a giant like Jupiter, and it does not describe a rocky terrestrial planet like Earth or Mars. It points instead toward an intermediate class, larger than Earth, smaller than Neptune, and shaped by deep cold and slow cooling. In plain terms, Planet 9 is usually imagined as a super-Earth or a small ice giant. Super-Earth simply means a planet more massive than Earth, but far below the size of the largest giants. Ice giant does not mean a world made of solid ice from top to bottom. In planetary science, the term refers to planets whose bulk material includes large amounts of water, ammonia, and methane compounds mixed with rock, wrapped in hydrogen and helium gas. Uranus and Neptune are the known examples in the solar system. Planet 9, if real, is often modelled as a smaller relative of that same family. Its mass is one of the most important clues. Current estimates generally place it near 5 to 10 Earth masses, with some recent orbital modelling favouring a value a little above 6 Earth masses. A planet in that range is too massive to be an ordinary terrestrial world. Under its own gravity, it would likely hold a gaseous outer layer. At the same time, it would still be much less massive than Uranus or Neptune. This middle status matters because it gives the planet a mixed character. It is heavy enough to retain gas and internal heat, yet modest enough that its structure may differ from the larger ice giants. Its radius remains uncertain because radius depends not only on mass but also on composition. A planet with more hydrogen and helium swells to a larger size. A planet with less gas and more rock remains more compact. Thermal evolution models therefore give a range rather than a single number. In many plausible cases, Planet 9 would measure a few times Earth's radius. That places it clearly above the rocky planets, but not among the swollen gas giants. The result is a world that would likely look, in broad planetary terms, like a subdued version of Neptune rather than a distant duplicate of Earth. The temperature structure of such a planet is especially interesting because deep distance from the Sun does not simply make it inert. The sunlight falling on a world hundreds of astronomical units away is extremely weak. If solar heating were the only source of energy, the planet would settle near the most severe cold of interplanetary space. But planetary models indicate that a world in the proposed mass range can still give off internal heat, left over from formation and slow contraction. This means its effective temperature may remain much higher than the tiny equilibrium temperature set by sunlight alone. In this picture, Planet 9 is not warm in any ordinary sense, but it is not merely a passive frozen stone. It is a cooling planet with a lingering inner energy budget. That distinction shapes the atmosphere. At such low temperatures, methane is expected to condense out of the upper atmosphere much more readily than it does on Neptune. This changes the chemistry of the outer layers. Instead of a simple scaled copy of Neptune's familiar methane-rich atmosphere, Planet 9 could have an upper atmosphere depleted in methane gas because much of that methane has dropped into cloud layers below. Hydrogen and helium would still dominate the gas, but the atmosphere would be altered by the cold. Clouds become part of this picture as well. In a very cold hydrogen-helium atmosphere, methane can form cloud decks, and deeper layers may include other condensed materials depending on pressure and temperature. The atmosphere would likely be stratified, with different substances stable at different heights. Yet because the planet remains only hypothetical, no one can describe these layers with certainty. It remains uncertain how deep the gaseous envelope is, how efficiently heat moves upward through it, and how much methane stays mixed above the cloud tops. Beneath the atmosphere, the interior is also unlikely to be a frozen solid globe. This is one of the most important corrections to ordinary imagination. On Earth, ice means a hard surface material. In the deep interiors of ice giants, the same substances exist under such enormous pressure and temperature that they no longer behave like ordinary ice. They form dense hot fluids and exotic high-pressure phases. So when Planet 9 is described as an ice giant, that phrase refers mainly to composition, not to surface appearance. The deeper interior would most likely consist of compressed mixtures of water-rich material, rock, and perhaps a central core of denser, heavy elements. Because the planet would cool slowly over billions of years, its present structure may preserve a long memory of how it formed, the amount of gas it still carries, the strength of its internal heat flow, and the exact radius it now has all depend on its early history. A world that began with a somewhat thicker hydrogen-helium envelope may still be puffier today. A world that formed with less gas may now be denser and smaller. Even so, a consistent picture begins to emerge. Planet 9, if real, is probably not a bare rock and not a giant like Saturn. It is more likely a remote transitional world, one occupying the wide middle ground between terrestrial planet and full giant. It carries several Earth masses of material, probably holds a hydrogen-helium atmosphere, likely retains measurable internal heat, and probably resembles a colder, smaller cousin of Neptune, or a massive sub-Neptune known from exoplanet studies. Its upper air may be strongly shaped by methane condensation, and its deep interior may be fluid and compressed rather than rigid and frozen. This physical portrait matters because it turns the hypothesis into a planet in the ordinary scientific sense. It gives the proposed world mass, size, temperature, chemistry, and structure. Far from the Sun, it would still be a complete planet, with layers, heat flow, and a long planetary evolution unfolding in darkness. The outer solar system does not merely hide a point of gravity. If Planet 9 exists, it hides a real world, cold and quiet, yet physically complex all the same. A distant planet can fail to appear in visible light for a simple reason. It does not make enough light of its own, and the sunlight it receives becomes feeble long before any of it returns to Earth. In the region where Planet 9 is thought to move, visibility is governed by distance more than by size. A world may be large, round, massive, and entirely real, yet still send back so little sunlight that ordinary searching methods struggle to separate it from the dark. Visible discovery in the outer solar system usually begins with reflected light. Sunlight falls on a body. Some of that light is absorbed, and some is scattered back into space. The scattered fraction depends on albedo, a term for reflectivity. A bright icy surface has a high albedo. A dark weathered surface has a low one. But reflectivity alone does not determine whether an object is seen. The harsher factor is distance. The light reaching the body drops with the square of its distance from the sun. Then the tiny amount reflected toward Earth weakens again as it travels back through space. The combined effect is severe. For reflected sunlight, apparent brightness falls roughly with the fourth power of distance. That relation has practical consequences. If the same planet were placed twice as far from the Sun and observed from the inner solar system, its reflected brightness would become about 16 times weaker. At 3 times the distance, it would fall by about 81 times. At 10 times the distance, the drop would reach 10,000 times. Planet 9 is not thought to orbit a little beyond Neptune. It is thought to lie hundreds of astronomical units from the Sun. In that regime, the fourth power penalty turns distance into concealment. This is why the phrase backyard planet can mislead. In one sense, a planet within the solar system is far closer than stars or galaxies. In another sense, that closeness does not help if the object is cold, dark, and weakly illuminated. A nearby star is visible because it shines by nuclear fusion. A faraway galaxy may contain billions of stars whose total light can be collected by a large telescope. A distant outer planet must rely mainly on borrowed sunlight. Size helps, but only to a point. A larger planet presents a larger area to the Sun and can reflect more light overall. This is one reason Planet 9 remains easier to imagine than a much smaller body at the same distance. Yet a several Earth-mass planet is not automatically bright in the outer solar system. If its radius is only a few times that of Earth, the increase in reflecting area does not cancel the enormous loss produced by hundreds of astronomical units of distance. Surface and atmospheric character matter as well. A world with bright reflective clouds would be easier to see than one with a dark, muted exterior. But even generous assumptions about albedo do not rescue visible light detection once the distance becomes large enough. Models of Planet 9 have to allow for uncertainty in composition, cloud structure, and atmospheric chemistry. That uncertainty changes the predicted brightness, sometimes by a significant amount. Yet across plausible cases, the broad conclusion remains the same. Reflected sunlight from a planet so far away is expected to be extremely faint. The way telescopes search the sky adds another limit. A faint source is not found against a perfectly black background. It is found against a sky filled with stars, galaxies, detector noise, scattered light, and the subtle glow of dust in the solar system. At the magnitudes relevant to a distant planet, seeing is not simply a matter of pointing at empty darkness and waiting. Astronomers must distinguish a dim moving point from a dense field of fixed points and instrumental imperfections. Even a real object can be overlooked if it sits below the survey depth, inside a crowded star field, or near the detection threshold where false positives multiply. Movement does not always solve this. In many solar system surveys, motion helps identify nearby bodies because planets, asteroids, and comets shift relative to the background stars between images. But a very distant planet moves slowly. In visible light, it may be so faint that long exposures are needed, and during those observations its motion may be too small to stand out clearly. A source that is both dim and slow can hide among ordinary unresolved points of light. This helps explain a common misunderstanding. The fact that telescopes can image galaxies billions of light years away does not mean they should easily image every planet in the solar system. Galaxies are detected through the combined light of enormous stellar populations. A distant planet in visible light is a single weak reflector. The observing problem is fundamentally different. The relevant question is not whether astronomy can see far. It is whether astronomy can detect a specific kind of faint target under the rules of reflected illumination. There is also the issue of orbital chance. A planet on an elongated orbit does not spend equal time at all distances from the Sun. It moves faster when closer in and slower when farther out, so it lingers through the dimmest stretches of its path. Even if the orbit includes a relatively less unfavourable region for detection, the planet is statistically more likely to be found far from that region than within it. Visible light searches therefore face not only an intrinsic brightness problem, but also a timing problem. All of this means that the failure to see Planet 9 in ordinary reflected light is not surprising within the hypothesis itself. The planet may be large enough to shape the outer solar system and still be too dim for straightforward optical discovery. Distance weakens the incoming sunlight. Distance weakens the returning light. Uncertain reflectivity broadens the range of possible brightness. Slow motion reduces detectability. Crowded or incomplete surveys leave room for misses, so the visible search reaches a clear scientific limit. Reflected sunlight is the most intuitive way to imagine finding a planet, because that is how the bright familiar planets first enter human experience. But that intuition comes from the inner solar system, where sunlight remains abundant. Far beyond Neptune, the same method begins to fail. A real planet can recede into a regime where reflected light no longer offers an easy path to discovery. In that outer darkness, invisibility does not require mystery. It follows directly from the mathematics of light, the scale of the solar system, and the quiet remoteness of the world being sought. In the deep outer solar system, light from the sun becomes so weak that another kind of visibility begins to matter more. A planet does not only reflect light, it also gives off heat. Any body above absolute zero emits radiation, and cold planets do so most strongly at long wavelengths beyond visible light. This is the basis of the infrared search for Planet 9. If reflected sunlight fails, the planet may still be found by the faint warmth it releases into space. The idea begins with the distinction between borrowed light and native heat. Borrowed light is sunlight that strikes a planet and is sent back toward a telescope. Native heat is energy the planet carries within itself and slowly loses over time. In the inner solar system, reflected sunlight is often the easier signal to imagine because the sun is bright and nearby planets are well lit. In the far outer system, that logic weakens. A planet hundreds of astronomical units from the sun receives very little solar energy. But if it is a several Earth mass world with a thick atmosphere and a deep interior, it may still retain heat left over from formation and gradual compression. That heat is not large by everyday standards, yet in the outer darkness it can become scientifically important. This changes the balance of detectability. Reflected light fades very rapidly with distance because sunlight must first travel outward to the planet and then return to the observer. Thermal radiation behaves differently. The planet emits its own energy, and that radiation only needs to travel one way to reach a telescope. The signal still weakens with distance, and it remains faint, but it does not suffer the same severe penalty that governs reflected sunlight. In simple terms, a distant planet can be easier to find through its warmth than through its shine, even though both signals are weak. For Planet 9, this possibility is strengthened by the kind of planet it is thought to be. Current models do not picture it as a small frozen rock. They picture a world several times the mass of Earth, probably with a hydrogen and helium atmosphere and a substantial reservoir of internal energy. Such a planet cools slowly. Over billions of years it radiates heat away, but it does not become thermally silent. The outer layers may be extremely cold, yet the whole planet can still emit more energy than it receives from the sun. In that sense, Planet 9 would not merely sit in darkness, It would glow faintly through its own slow cooling. At the temperatures thought plausible for such a world, the emitted radiation would lie mainly in the infrared, especially the far infrared. This is the region of the spectrum associated with cold objects. Human eyes cannot see it, but specially designed detectors can. Telescopes built for infrared astronomy do not search for bright blue or white points. They search for weak heat signatures spread across long wavelengths. In this regime, the planet would not look like a familiar visible planet at all. It would appear as a dim infrared source, easy to confuse with many other kinds of astronomical objects unless its motion and colour are measured carefully. The probable temperature of Planet 9 remains uncertain because it depends on mass, composition, atmosphere, and age. Still, current studies generally place it only a few tens of degrees above absolute zero. That is bitterly cold, yet still warm enough to produce measurable far infrared emission under favourable conditions. The important point is not the exact temperature. The important point is that internal heat may dominate over sunlight in determining the planet's thermal output. This gives infrared searchers a logical advantage. They are not waiting for weak sunlight to bounce back from a distant cloud deck. They are looking for the planet's own quiet energy loss. This also means that the search is closely tied to planetary evolution. A younger or more massive planet may retain more internal heat, and therefore shine a little more strongly in infrared wavelengths. A planet with a different atmospheric structure may release energy differently across the spectrum. Methane condensation, expected in such a cold atmosphere, can alter how radiation escapes from upper layers. Cloud decks can also affect the emitted spectrum by changing where in the atmosphere the radiation last emerges, even without a direct detection. This makes Planet 9 a physically rich object to model. Its possible infrared brightness is not only a search problem, it is also a clue to what the planet would be like as a world. Yet infrared does not solve the problem completely. The signal remains weak, and the sky at these wavelengths is not empty. Cold dust in the solar system and beyond it also glows in infrared light. Distant galaxies can appear as faint infrared points. Survey instruments have limited sharpness, and many sources in the sky can blur together or remain poorly localized. A true planet may therefore hide not because it is invisible in principle, but because it is difficult to distinguish from the many other dim things that infrared telescopes already record. Another complication comes from time. A far infrared survey may record a source at one date, but unless that source is seen again after enough time has passed, it may be impossible to tell whether it is a moving solar system body or a fixed distant background object. This is why repeated surveys separated by many years become valuable. A real distant planet should drift slowly across the sky. If two all-sky infrared maps taken decades apart both show a faint source in slightly shifted positions, that pairing can become a serious candidate for follow-up. Recent work using the IRMAS and Akari all-sky surveys is built on exactly this principle, and it has produced candidate sources rather than a confirmed planet. The infrared search therefore occupies a careful middle ground between promise and limitation. It is more physically favourable than visible light searching in one important respect, because the planet's own internal heat may remain detectable when reflected sunlight has become too faint. But it is also demanding because the planet is still very cold, still very far away, and still immersed in a sky full of other infrared emitters. Every candidate must be filtered through motion, colour, and consistency with the expected brightness of a distant cooling planet. So heat in the darkness does not make Planet 9 easy to find. It simply changes the terms of the search. Instead of asking where sunlight might reveal a remote world, astronomers ask where a cold planet's own lingering warmth might rise just above the threshold of detection. In the outer solar system, that faint warmth may be the more truthful signal. It is weak, patient, and difficult to isolate, but it belongs to the planet itself. If Planet 9 is ever first recognized not as a reflected point of light, but as a dim source of far infrared glow, that discovery will follow directly from the simple fact that even a very cold world is never perfectly dark. A planet in the far outer solar system does not reveal itself on the sky in the same manner as a nearby asteroid or one of the known major planets. It moves, but it moves in a way that is easy to underestimate and easy to miss. Against the fixed background of stars, a very distant planet can appear almost still. This does not mean it lacks an orbit. It means the scale of that orbit is so large, and the pace of its progress along that orbit is so slow, that its true motion becomes difficult to notice over ordinary observing intervals. In the search for Planet 9, this near stillness is one of the central practical obstacles. Any solar system body has apparent motion on the sky for two main reasons. One is its own travel around the Sun, the other is Earth's travel around the Sun, which changes the observer's point of view through the year. That second effect is called parallax. Parallax is the apparent shift in position of a nearby object when seen from different vantage points. It is familiar in simple human experience, where a nearby object seems to shift against a distant background if the observer changes position. In astronomy, Earth itself provides the changing viewpoint as it moves through its yearly orbit. For a distant planet like the one proposed, both effects are present, but they do not contribute equally. The planet's own orbital motion is extremely slow because its orbit is vast and its period is measured in many thousands of years. Over a single night, or even over many nights, that true motion across the sky can be very small. Recent search work emphasizes exactly this point. At the distances generally considered for Planet 9, proper motion, meaning the planet's real angular movement from its own orbit, is expected to be minimal compared with nearer solar system bodies. What often matters more in practice is parallax, the apparent shift imposed by Earth's changing position. This creates an unusual observing situation. A distant planet is not fully motionless, yet it may fail the ordinary visual test by which moving solar system objects are often found. Many asteroid searches rely on obvious displacement from one exposure to the next, or from one night to the next. A nearby asteroid may betray itself quickly because it slides noticeably across the star field. Planet 9 would not behave that way. Its nightly motion could be so slight that it blends into the large population of faint point sources already present in deep images. If astronomers are searching with methods tuned for faster targets, a very distant planet may remain hidden inside the category of things that seem fixed. Parallax helps, but only when used deliberately. Because Earth moves around the Sun, a distant outer planet should shift position slowly against the background stars over months. Current Planet 9 studies describe that effect as measurable in principle, yet still modest in size. Recent infrared search papers estimate that for the distances often proposed, parallax over half a year would amount to only a few tens of arc minutes, while the planet's own proper motion would be smaller still. In other words, the dominant visible change across moderate timescales may come not from the planet sweeping around the Sun, but from Earth changing the line of sight. That fact changes how a search must be designed. The goal is not simply to detect a faint point. It is to detect a faint point whose displacement over time matches the slow pattern expected for a body hundreds of astronomical units away. This is why repeated imaging, careful astrometric comparison, and long baseline survey matching becomes so important. Astrometry is the precise measurement of positions on the sky. For a nearby fast-moving object, moderate positional precision may be enough. For a distant planet whose movement is slight, the position measurements must be stable and the image registration must be extremely careful. A false shift caused by instrument effects, atmospheric variation, or image distortion can imitate motion. A real shift can be small enough to be buried by the same sources of error. The direction of the apparent motion matters too. At opposition, when a body lies roughly opposite the Sun in Earth's sky, parallax can make its short-term motion easier to detect because the viewing geometry is favourable. Earlier work on Planet 9 emphasised that under such conditions, motion driven mainly by parallax might be measurable even within a day for some allowed distances and brightness levels. Yet this does not make detection simple. A source first has to be identified as a plausible planet candidate rather than an ordinary background point, and then it has to remain visible with sufficient clarity in repeat imaging to confirm the shift. The motion is available as a clue, but only if the object is already near the threshold of recognition. This is one reason a real planet can remain hidden in archival data. A distant planet may already appear in images taken years ago, but without an obvious trail or rapid displacement. It may have been recorded as an unremarkable faint source. If the survey is not specifically arranged to compare positions across the correct span of time, the object can sit unnoticed among immense catalogues of stars and galaxies. Only later, when a candidate's search region is narrowed, or when decades-separated surveys are cross-matched, does the possibility arise that a slowly shifting point might be recovered. The problem is therefore not only detection in the moment, it is also recognition after the fact. Motion that is too slow creates another difficulty. A source may look almost stationary within one observing season, and yet still move enough across longer intervals to fail straightforward catalogue matching. It can therefore occupy an awkward middle ground. It is not still enough to behave like a permanent background star, and not mobile enough to announce itself like an asteroid. Search strategies have to account for this intermediate behavior. Recent targeted searches explicitly use the expectation of minimal motion over consecutive nights and modest parallax shifts over longer baselines as part of their candidate selection. All of this means that the sky does not simply hide Planet 9 through faintness alone. It also hides it through tempo. The planet would move on a timescale that resists casual noticing. Human intuition is poorly suited to this regime. A world inside the solar system is expected to wander plainly against the stars, but a world hundreds of astronomical units away wanders with extraordinary restraint. Night to night it may seem fixed. Month to month it may shift only a little. Year to year it may finally begin to separate itself from the background in a measurable way, though still delicately. So motion against the stars becomes both the problem and the method. It is a problem because the motion is too slow for ordinary moving object searches. It is a method because the right kind of slow motion can distinguish a true distant planet from the vast number of fixed sources on the sky. Planet 9, if it exists, does not race into view. It drifts. Its own orbital progress is almost silent, and Earth's changing viewpoint supplies much of the observable shift. In the search for such a world, astronomy is not watching for speed. It is watching for the faintest, most patient displacement that a distant planet can make. A distant planet is not searched for in abstract darkness. it is searched for on the real sky, and the real sky is uneven. Some regions are comparatively clean and open, with fewer stars and less confusion. Other regions are crowded, bright, and difficult, filled with so many sources that a faint moving object can disappear into the background. This is one of the most practical reasons Planet 9 can remain hidden. Even if astronomers have a broad idea of its likely brightness and motion, the sky itself does not present every possible location with equal clarity. The Milky Way is central to this difficulty. From Earth, the plane of the galaxy appears as a dense band of stars, dust, and unresolved light stretching across the sky. In that band, the number of visible sources rises sharply. A faint point that would stand out in a sparse field can become hard to separate from the crowded stellar background. The problem is not merely that there is more light overall. The problem is that there are many more distinct points of light, more overlapping source profiles, and more chances for false detections or missed detections. Planet 9, if it lies in or near such a region, would have to be identified inside one of the busiest parts of the sky. Recent search studies make this point plainly. A targeted parallax-based search published in early 2026 describes one of its chosen fields as a high-probability region that had remained only weakly constrained in part because of severe source crowding near the galactic plane. The same study notes that scattered light from bright stars can spoil the position of a candidate on one or more nights. Another major pan-stars search concludes that the remaining allowed parameter space for Planet 9 is concentrated strongly in the galactic plane, and that objects there are biased against discovery because available images in those regions are less favourable for secure detection. These are not speculative difficulties. They are observed limits of real survey work. Crowding changes the search in several ways at once. First, it raises the number of background sources that any automated pipeline must consider. A survey looking for a faint, slowly shifting planet may begin with millions of detected points. Most of them are ordinary stars, galaxies, or artifacts of the instrument. In a crowded field, the number of combinations that can imitate plausible motion grows quickly. Second, the brightness pattern of neighbouring stars can distort the measured position or brightness of a faint source. Third, bright stars create halos, diffraction patterns, and scattered light that can mask nearby objects entirely. A planet does not need to be intrinsically invisible to be lost. It only needs to occupy a difficult patch of sky. The sky is also uneven because surveys are uneven. Many wide-field programs are designed for scientific goals other than finding Planet 9. They may aim to discover supernova, mate up galaxies, or detect nearer solar system bodies. For those purposes, the densest parts of the Milky Way can be inconvenient. Source confusion is higher there. Image subtraction is more difficult, and the rate of false positives rises. As a result, some surveys naturally avoid those regions, sample them less often, or collect fewer exposures of usable depth there. This produces observational holes. A faint outer planet can persist not because no one looks anywhere, but because the most difficult sky has historically been the least thoroughly searched for that particular kind of target. Season also enters the problem. No telescope on Earth observes every sky region at all times of year. As Earth moves around the Sun, a given region becomes accessible at night for a period, then drifts into bright evening twilight, then too near the Sun for practical observation, and later returns to the night sky again. This means Planet 9 searches operate through windows. If a promising region is visible for only part of the year, repeated confirmation images may have to wait months. A candidate faint source can therefore remain unresolved for long intervals simply because the geometry of Earth and Sun closes the observing window. The search advances in seasons rather than continuously. Infrared all-sky surveys illustrate this especially well. WISE, for example, scans the sky while maintaining a nearly fixed solar elongation, meaning it observes at a stable angle from the Sun rather than pointing arbitrarily anywhere at any time. In that geometry, a typical sky location is revisited at roughly 6-month intervals instead of being watched continuously. This creates repeated observing seasons separated by long gaps. Those seasons are useful for parallax and motion studies, but they also mean that a candidate cannot be tracked at will. Sky visibility is built into the survey architecture itself. The planet must wait for the telescope's geometry as much as the telescope waits for the planet. Difficult sky also includes more subtle forms of inconvenience. A predicted search region may lie low above the horizon for some observatories, increasing atmospheric blur and reducing sensitivity. It may overlap with moonlit conditions during key nights. It may contain so many bright stars that the effective area of clean, searchable sky shrinks. It may fall in a region where archival data exist, but not in the right filters, or not with enough repeat visits, or not with image quality sufficient for slow-motion detection. In planetary searches, absence of coverage is rarely absolute. More often, it is a matter of coverage being too shallow, too sparse, or too contaminated to be decisive. This means that the sky itself becomes part of the explanation for non-detection. Planet 9 is not only distant and faint, it may also occupy a part of the celestial sphere where the usual advantages of modern surveys weaken. The hardest remaining regions are not random. They are places where the galaxy is bright, the fields are crowded, the observing cadence is imperfect, and the available data leave room for a slow, dim source to pass unnoticed. So the search narrows not only by orbital theory, brightness estimates, or motion models, but by terrain. Astronomers are no longer scanning a uniform dome. They are working across a landscape with crowded valleys, bright obstacles, seasonal closures, and thinly mapped zones. In the logic of the Planet 9 hypothesis, this is not a minor detail. It is one of the main reasons the planet can still be both plausible and unseen. A real world can remain hidden simply because the sky around it is difficult, by this stage in the search. The absence of a discovery does not mean that nothing's been learned. The opposite is true. Modern surveys have removed large portions of the most plausible search space for Planet 9. The search is no longer a broad sweep across the whole sky. It has become a process of exclusion. Wide-field optical surveys, repeated time-domain programs, and infrared archives have tested many of the places where a planet with favoured characteristics would have been expected to appear. Each non-detection narrows the range of positions, distances, and brightnesses that remain compatible with the hypothesis. This narrowing must be described carefully. Surveys do not rule out every imaginable Planet 9. They rule out parts of a specific family of predictions. Those predictions come from the dynamical models used to infer the planet's likely mass, orbit, and present location from the behavior of distant trans-Neptunian objects. Researchers often generate a synthetic population, meaning a large set of simulated Planet 9s drawn from the allowed orbital ranges of the model. They then ask which of those simulated planets would have fallen inside the footprint, depth, and cadence of a real survey. If many of those simulated worlds should have been seen but were not, then that fraction of the modelled parameter space can be excluded. The logic is statistical, not absolute. One of the first large exclusions comes from the Zwicky Transient Facility. That search uses a wide northern sky archive and concludes that, for the brown and Batygin reference population, about 56% of the predicted phase space is ruled out. The importance of that result is not only the percentage itself, but the kind of planets it removes. Brighter and generally closer versions of the modelled planet become much less likely if they would have crossed the survey area at detectable magnitudes and yet remained unseen. The dark energy survey extends this process in the south. Using the 6-year survey footprint and a simulator designed for distant solar system bodies, researchers test which members of the same synthetic population would have passed through the observed region and been recoverable. That analysis finds that the dark energy survey removes an additional slice of the remaining modelled space, roughly 5% beyond what would already have been excluded by the Zwicky Transient Facility alone. This matters because the survey reaches deeply and covers a different part of the sky. Then Pan-STARRS adds another major layer, the Pan-STARRS. One search uses the second data release of the survey and concludes that, when combined with earlier Zwicky Transient Facility and dark energy survey constraints, about 78% of the brown and Batygin parameter space is ruled out. This is a striking number, but again it needs interpretation. It does not mean that 78% of all possible hidden planets beyond Neptune have been disproved. It means that nearly 4/5 of the allowed positions for a planet matching that modelled family are no longer consistent with the available survey data. What do these exclusions remove in physical terms? They preferentially remove planets that are bright enough and located in areas where existing surveys are effective. A world nearer perihelion, somewhat closer to the Sun, or lying in a well-covered region of the sky is more vulnerable to exclusion, a world near aphelion. Much farther away, or hidden in difficult fields, survives longer. In this sense, every successful null survey reshapes the surviving portrait of Planet 9. The remaining hypothetical planet becomes less like an accessible optical target and more like a faint object living in the hardest parts of the search space. Brightness limits help illustrate this. The Zwicky Transient Facility search reaches roughly to visual magnitude 20.5, with high efficiency for the motion regime. The Pan-STARRS search reaches deeper, to a 50% completion depth, near visual magnitude 21.5. That deeper reach removes many sources that would have been too faint for shallower work. Yet even this does not exhaust the predicted brightness range. Simulated planets in the favoured orbital families can extend to much fainter apparent magnitudes, depending on size, albedo, and distance. The remaining space is not random. Pan-STARRS reports that much of what is left lies at magnitudes fainter than about 21, and in regions near the northern galactic plane, where the ecliptic crosses dense stellar fields. This conclusion is important because it joins two difficulties together. The planet may be faint, and the sky around it may be crowded. A target that is only barely detectable in a clean field may become effectively invisible in a complex one. The surviving search space is therefore not merely smaller, it is more stubborn. Infrared work adds a different kind of constraint. Because Planet 9 may emit detectable heat, all sky infrared data from missions such as IRAS, Akari, WISE, and NEOWISE help test whether a slow-moving thermal source already appears in archival surveys. These searches have not produced a confirmed discovery. They do, however, remove some thermal possibilities and identify candidate sources that require follow-up. Here too the same rule applies. A null result does not erase the hypothesis, but it trims the combinations of distance, temperature, and sky position that remain open. NASA's summary reflects the present state well. The planet remains theoretical. There is debate over whether it exists, and the evidence is indirect. At the same time, the search has become more disciplined than it was when the hypothesis was first proposed. The likely orbit is not free to run anywhere. Large areas of predicted sky position have now been tested with enough depth that a substantial fraction of the favoured orbital solutions has been removed. This is why survey exclusion is so scientifically valuable. A non-detection can look empty from the outside, but in astronomy it often acts like measurement. By showing where the planet is not, surveys refine what the planet would have to be if it is real. The surviving options shift toward dimmer, more distant, more slowly moving, and more observationally inconvenient configurations. So the darkness around Planet 9 is no longer broad in the way it once was. It is narrowing into specific kinds of darkness. Much of the easy territory has been taken away by wide-field surveys. What remains is a smaller and more difficult residue tied to faintness, crowding, and incomplete coverage. The search does not stand where it began. It stands after years of subtraction. If Planet 9 is real, it is increasingly forced to live only where the surveys have not yet been strong enough to erase it. Once much of the easier search space has been removed, the hunt for Planet 9 changes character. It becomes less like a broad survey of possibility and more like a patient campaign of method. The remaining task is not simply to look harder in the same way. It is to combine several kinds of looking, each designed for a different weakness of the planet's signal. A distant world may be too faint in reflected light, too slow for standard moving object searches, too crowded by the galactic plane, or too uncertain in present location for any one telescope to find quickly on its own. The search therefore continues through a layered approach. Astronomers return to the same fields, compare present observations with old data, track tiny positional shifts, and test visible candidates against infrared expectations. Repeated deep imaging is one part of this process. A deep image is an exposure sensitive enough to record very faint sources. One deep image alone can reveal a candidate point of light, but it cannot easily say what that point is. It may be a star, a galaxy, detect a noise, or a planet. Repetition is what gives the image scientific value for Planet 9. When a field is imaged again and again, astronomers can compare the positions of faint sources over time and look for the particular kind of motion expected from a body hundreds of astronomical units away. A source that remains perfectly fixed belongs to the distant background. A source that shifts too quickly is more likely a nearer solar system body. The target is the small middle range, a point that moves slowly enough to be compatible with a distant planet and consistently enough to survive scrutiny. The quality of the images matters as much as the number of them. A search for Planet 9 cannot rely on casual repetition alone. The images must be deep, well calibrated, and aligned carefully enough that tiny shifts on the sky can be measured without confusion from atmospheric blur or optical distortion. This is why dedicated observational campaigns remain valuable even in an age of large public archives. Recent targeted searches use consecutive night imaging to exploit parallax, the apparent shift caused by Earth's changing position, because a very distant planet may show just enough displacement between nights to separate itself from fixed sources when the data are precise. The motion is small, but precision turns small motion into a usable signature. Archival comparisons form another major method. The modern sky has already been photographed many times by many instruments for many purposes. Those past images become a hidden resource once the Planet 9 search is narrowed to likely regions or expected motion regimes. A source that seemed unremarkable in an old survey can become interesting when paired with newer data. The logic is simple. A distant planet is slow, but not truly fixed. If an object appears in an old image and then appears slightly displaced in a later survey taken years or decades afterward, it becomes a candidate for further testing. This is especially useful because long baselines strengthen the motion signal. A shift too small to notice overnight may become clear over 20 years. That is why comparisons across surveys are now central to the search. Infrared studies using IRAS and ACARI rely on a 23-year separation between all sky maps, long enough for a plausible Planet 9 to drift measurably while still remaining within the motion range expected for a distant-bound planet. Optical archives serve a similar role when they are deep enough and when the fields overlap the surviving search space. The search, therefore, proceeds through time as much as through space. Astronomers are not only scanning the present sky, they are reconstructing its changes across decades. Parallax-guided targeting adds another level of refinement. Parallax is especially useful because the motion of a distant planet on the sky can be dominated not by its own orbital progress, which is very slow, but by Earth's annual motion around the Sun. This means a field can be searched with a specific prediction in mind. If the planet lies at a certain distance, then over a given interval, its apparent displacement should fall within a narrow range and should point in a predictable direction. Candidate selection can therefore be guided not merely by brightness, but by motion geometry. A faint source is more interesting when its shift matches the expected parallax of a remote planet. This method reduces the enormous number of false positives that naturally arise in crowded or noisy data. Many faint detections are not planets at all. Some are image artifacts, some are variable stars, some are galaxies whose measured positions fluctuate slightly under changing conditions. Parallax-guided filtering imposes a physical rule on the search. It asks not whether a point moved somehow, but whether it moved in the way a distant planet should. This is one reason recent targeted searches can work effectively even in difficult sky regions. They do not treat every source equally. They search for a narrow behavior. Infrared checking remains essential because visible light candidates can be misleading. A source that looks promising in optical images may still fail the physical test if its brightness, color, or absence at thermal wavelengths does not fit a cold several Earth mass planet. The same is true in reverse. A faint infrared source may seem attractive, but unless it also behaves like a slow-moving solar system body rather than a distant galaxy or dusty background object, it cannot carry the claim far. Planet 9 searching therefore increasingly depends on multi-method consistency. A candidate becomes persuasive only when it survives across different kinds of data. This is also where large survey infrastructure helps. Pan-STARRS, the Dark Energy Survey, Zwicky Transient Facility, WISE, NEOWISE, IRAS, and ACARI do not contribute in identical ways, but together they create a layered observing system. Wide optical surveys remove bright and accessible possibilities. Infrared all-sky maps test for faint thermal sources. Dedicated follow-up campaigns return to narrowed fields with deeper or more precise observations. Public and professional efforts can also meet here. NASA's Backyard Worlds project reflects the same principle on a broader scale, turning repeated infrared imaging into a motion search that can reveal cold, faint nearby bodies through careful visual or automated comparison. The search continues. Then, by increasing coherence, Early discussion of Planet 9 begins with dynamical hints and broad predicted regions. The present stage is more disciplined. Observers use models to choose where to look, archives to extend the time baseline, repeated deep imaging to capture minute motion, and infrared data to test physical plausibility. Every method answers a different weakness in the planet's detectability. No single method is sufficient by itself, but together they narrow the darkness. So the continuing hunt is not blind persistence, it is structured persistence. It accepts that the planet, if real, is likely faint, slow, and hidden in difficult sky. It answers faintness with depth, slowness with time baselines, uncertainty with targeting, and ambiguity with cross-checking across wavelengths. In that way, the search becomes increasingly exact. Planet 9 remains unseen, but the methods pursuing it now fit the problem more closely than before. The outer solar system is not yielding quickly, yet it is being examined with growing precision, one field, one archive, one measured shift at a time. At the present edge of the question, the Planet 9 hypothesis stands in a measured state between attraction and restraint. It has not faded away, because the dynamical arguments that gave rise to it have not been decisively erased. Yet it has not hardened into accepted planetary fact, because the planet itself remains unseen and the orbital evidence remains debated. This balance defines the scientific situation more accurately than either certainty or dismissal. Planet 9 is neither a discovered world awaiting a name nor an abandoned curiosity from a brief moment of excitement. It is an active hypothesis under pressure from both observation and criticism. NASA's current language captures this balance with care. The planet remains theoretical. That single word matters. It means the idea is grounded enough to justify continued search, modelling, and discussion, but not secure enough to enter the solar system as an established member. The outer solar system does contain real orbital puzzles. Some distant bodies appear unusually detached. Some orbital directions remain suggestive. Long-term dynamical models show that a distant several Earth-mass planet can in principle reproduce important parts of this pattern. At the same time, none of those facts amount to direct detection. The hypothesis lives by inference, and inference in astronomy can be powerful without being final. What has changed over the years is not the basic status of the planet, but the discipline with which that status is now defined. In the earliest public phase of the idea, much attention focused on the dramatic possibility that a large hidden world might be waiting in the far outer solar system. That possibility still exists, but it is no longer broad and romantic in the same way. Survey work has narrowed it. Statistical criticism has tested it. Search teams have learned more about where the planet is unlikely to be, how faint it might be, and what kinds of sky remain hardest to search. The hypothesis has become less expansive and more exact. This is often how science matures around a difficult object. The question becomes sharper before it becomes answered. A theory that first appears as a striking general explanation is gradually forced into narrower boundaries. It must match what the sky reveals and what the sky refuses to reveal. Planet 9 now occupies this narrowed condition. If it exists, it is increasingly constrained to a smaller range of distances, brightnesses, and search regions than before. Much of the easy optical space has already been tested. Much of the remaining parameter space appears to lie in faint magnitudes and difficult stellar fields, especially near the galactic plane. This does not prove the planet is there. It only means that if it survives the present level of scrutiny, it survives in the hardest corners of the problem. The debate over orbital clustering remains central because it controls how much weight the rest of the search should carry. If the clustering of extreme trans-Neptunian objects is mostly physical, then a distant planet remains one of the strongest available explanations. If the clustering weakens substantially, once observational bias is modelled more completely, then the motivation for the hypothesis diminishes. This is why every new distant object matters twice. It adds to the population itself, and it also changes the statistics used to judge whether the pattern is real. The case for Planet 9 is therefore unusually sensitive to the growth of the sample. Discovery and interpretation remain tightly linked. Recent infrared work has added an interesting but still incomplete layer to the story. Candidate sources found through comparisons of all-sky far-infrared surveys show that the search is not exhausted and that a plausible thermal signal can still emerge from old data. But a candidate is not a planet. A pair of detections at separated epochs, even when consistent with a slow-moving distant body, does not provide a secure orbit on its own. Follow-up is required. This is another example of the present state of the hypothesis. The evidence has enough structure to keep the search alive, but not enough to close it. The most likely future of the question, therefore, lies not in argument alone, but in new surveys. The Vera C, Rubin Observatory is especially important in this respect. Its wide, deep, repeated imaging of the southern sky is expected to transform the inventory of distant solar system objects and improve the search for slow, faint planets. Even if Rubin never images Planet 9 directly, it can still change the debate profoundly by discovering many more distant trans-Neptunian objects. A larger and better characterized outer population will test whether the reported clustering strengthens into a more convincing structure, or dissolves into a pattern produced by small numbers and uneven discovery. In that sense, Rubin may help decide the hypothesis either by finding the planet or by changing the evidence that made the planet seem necessary in the first place. This is why the current scientific position is best described as disciplined uncertainty. Observations indicate that the idea remains plausible within a shrinking but not yet empty space of possibilities. It remains uncertain whether the distant orbital patterns require an unseen planet, or whether they can ultimately be explained through bias, early solar system history, or a combination of weaker effects. That uncertainty is not a flaw in the subject. It is the correct shape of the evidence. For the outer solar system itself, this state of uncertainty is revealing. It shows that the Sun's planetary domain is still not fully mapped in the intuitive human sense. The major planets are known, yet the system's farthest architecture remains partly inferential. Small icy bodies still act as messengers from regions that are too dim and too slow to yield their contents quickly. In that environment, a hidden planet remains conceivable not because science is careless, but because the solar system is large enough and dark enough to support such a possibility for a long time. So Planet 9 comes to rest, for now, as a hypothesis with real explanatory power and real observational difficulty. It is more constrained than when it first entered public attention, but not eliminated. It is more physically modelled than before, but still undetected. It continues to stand where good scientific ideas often stand before resolution exposed to criticism, tested by new data, and waiting for the sky to decide. If a planet is there, the case will sharpen until the world itself is seen. If no planet is there, this same process will gradually strip the hypothesis of its necessity. For the present, the honest conclusion is quiet. Planet 9 could be real. The evidence is not yet enough to say that it is. Far from the bright inner planets, the solar system grows quiet again. The thought of a hidden world remains there in the dark, not as a fantasy, but as a measured possibility shaped by distance, faintness, and time. The sun still holds that remote region within its reach, yet it lights it only weakly. Small icy bodies continue their long path through cold space, carrying slow records of gravity in their motion. Astronomers continue to read those records with patience, knowing that absence of a direct image is not the same as absence of a world. In this outer silence, the search remains careful. It does not rush towards certainty. It follows light where light is available, heat where heat may still escape, and motion where motion is almost too small to notice. It accepts that the sky can conceal real things for very long spans, especially when those things move slowly and live far from warmth. It also accepts that nature does not owe a simple answer. A pattern may strengthen, a pattern may fade, a candidate may endure or disappear. The work continues in that calm middle ground where science is most honest. So the distant edge of the solar system remains partly known and partly withheld. It is mapped by the worlds that have been found, and by the empty places where no world has yet appeared. It is described by careful models, and corrected by every new observation. If Planet 9 is there, it remains only a little longer in darkness. If it is not there, the same slow search will reveal that too. Either way, the outer solar system keeps its measured dignity, wide and cold and patient, asking only for time, precision, and a steady gaze.